Hello everybody, welcome to the March Queensland AI meetup. It's been a little while between drinks, but we are joined tonight by Juxi, who's, I think a lot of you actually might know of. He's well known around the traps. If you've spent time at QUT or in robotics, you've probably heard of Juxi. And I think you've also been involved in some of the early Queensland AI meetups as well, which is great. So good to have you back as a speaker. He's going to tell us all about some of the work that he and the team at Lyro Robotics are doing, some of the applications and current challenges in the space and where it's moving. We will have a bit of time at the end as well for some Q&A, so if you do have any questions, keep those and we'll ask them later. Over to you, Juxi.
Thank you. Awesome. Yeah, I have some slides about that. But I like interactive sessions. So if you have questions, please ask them. We'll get a microphone to you because this is recorded and nobody hears you on the recording if you don't wait for the microphone. So just keep that in mind, but feel free to ask questions. Thanks for having me and thanks for the intro. It's been good to be back here. It's been a while. I guess we are getting used to Zoom meetings, but it's very nice to see people face to face. I'm glad to be here. Today I will talk about what we do at Lyro Robotics and some of the challenges that we faced and some of the, I guess, hard problems that come up when you are trying to build embodied AI systems. We are a robotics company, an AI-enabled robotics company, but in the end we are a robotics company and not an AI company, right? So keep that in mind. It might not be directly applicable to you, but I hope there's something that you can learn out of that. And I'm trying to do sort of, I guess, three things. One is like, how do we design our systems? How do we build them? How do we scale them? Again, embodied AI systems. A few of the lessons learned. So I have a few slides in the middle that should tell some of the lessons learned. And again, more than happy to take some of the questions that you have and discuss them a bit further. And also a few comments or discussions, ideally, about the Australian ecosystem and how we do things differently in the broader scope and how we can maybe improve on that. All good? No. It's weird when somebody walks behind you. No, all good, mate. Cool. There will be robot videos. So, in case you get boring once in a while, just shout robot video and I can bring up another one. But one of the things that was brought up was, why does it seem to be so hard to solve certain problems? And I want to go a bit more into this, and it's a slightly different title slide here than it was on the meetup group, and that is partly intentional, partly not. But I really want to talk about why it's also important to solve very big problems and why that might lead to why some of these things seem hard, or at least, in the beginning seem very hard. Cool. So we are Lyro Robotics. We build robotic systems, in case that hasn't come across yet. But we are also really interested to understand what these systems can do for us. And what we're really interested in is building robotic systems that can really help us free people from the need to perform dirty, dull, and dangerous tasks. So things where people need to stick their hand in right now and do manual labor. The goal for us as a company is to get 100,000 robots out by the end of a decade. Like 100,000 robots, right? Not 1, 2, or 100, but 100,000. It's a very big goal, but I think it needs to happen. And COVID has shown us that there's a massive problem out there that's just been accelerated, but also I believe we can do that. And I believe we can do that here in Queensland. I don't think we have to go overseas. Obviously, to deploy 100,000 robots, you want to look at a global market, but we can really be at the forefront of that here, both on the robotics side of things and on the AI side of things. And that sort of ties in, I guess, with why some problems seem larger than others. This is a very big problem that we're trying to solve. And we're starting with the food supply chain, but in the whole supply chains, there's the question of how we, in the 21st century, secure, safe, and reliable way of getting products from where they're being produced to where they're being consumed. And that's a massive problem right now, right here. There was an EY report, I think it's now a couple of months old, but it's 26,000 jobs that are unfilled. And that's not just all backpackers, right? But like there's a lot of backpackers as well that are currently not here doing the jobs that need to get done so we can actually get, smashed avocado as an example. And that's a big problem, right? It's 26,000 jobs. One robot is not going to solve that. 2 robots is not going to solve that. And yes, I understand some of that might be COVID and people say, oh, it's going to be better when the borders are open. But first of all, this will be felt for years. The farmers that we talk to right now, they are worried that the food that they're planting right now, they don't know if they can harvest. They don't know if they can get it through a supply chain. They don't know what to do. And they are really worried. And that's really a big problem, right? Because if they start getting worried and just be on the safe side and plant less, that still increases the price at the end. And it still doesn't take the pressure off the supply chain. The other thing is that there's a consumer push. Right now, we as consumers are actually pushing and saying, well, can we get our produce without like 100 people touching it along the way? And yes, COVID is one thing, but it's the same thing with pesticides and herbicides and other contaminants. So it's a problem that's going to stick around for a while. And even if you don't believe that it's just an agriculture problem, it's the same thing in e-commerce. I guess I can ask for a show of hands, but who has ordered online over the last 12 months? There's one person who has not. No, just kidding. It is obviously a growing market, right? And we still have the same problem in e-commerce as much as in agriculture. How do we get the products from where they're being produced all the way to where they're being consumed? And so for us at Lyro, that's a clear signal that there's a need for 1,000 robots out there, right? It's not just one robot again, it's multiple that we need. And just to take it away, we have a solution for it, right? So over the last 12 months, we've focused on the agriculture supply chain and tried to build a system that can actually deal with that, and it cannot deal with that in a flexible way. So we have designed, developed, and deployed now the world's first fresh produce packing robotic system. That's a bit of a mouthful, I understand that. Oh, that somebody was applauding, thank you. But it's basically a robotic system that is not a specific machine that only works for avocados. It's a robot that works for avocados, lemon, lime, mango, passion fruit, chili, pineapples, sweet potatoes, and yesterday we also packed nectarines. So it really works for a wide range of fruit. And why is that important? Because they're seasonal, because they vary significantly between the deployments, but we still have the same problems across all of them. That means we need to have a robotic solution that can scale to all of that. And that's really what we did. This is more the customer slide. I understand this is a Queensland AI meetup, and I'm going to get into the AI very soon. But I think one of the problems that I've seen with AI companies and startups is AI is not the product, right? A lot of people are thinking that AI is the product, but it's not. AI is the enabling technology. AI is the thing that helps you build a scalable technology and a scalable product, but it is not the product itself. And that's why this slide is in here. For our customers, they couldn't care less if there's a black box full of whatever, random animals or whatever in there. They don't care about deep learning. They don't care about AI. They care that the produce goes in on one end and packed boxes go out on the other end. For us, part of this slide is actually the technology, right? So the plug and play, the pay-as-you-go option, that's all directly enabled by having an AI-enabled robotic system. But it's not a benefit that you can tell a farmer about, right? So they don't care, like your deep learning system is awesome and the best in the world. They care that in 10 minutes you can change from avocados to lemons. You can change in less than an hour, like a new robot on the line. That's really what's critical to them. And that's really, for me, I think a core point of that. So product development is slightly different from pure research. And I tried to put that a bit on a slide here. Like tech transfer is something that we should probably discuss in Australia, and it's a longer discussion. But for us, we're thinking about a problem, and you need to think about a problem, which usually then makes you think about a product, which then should make you think about a research. And I put that in that specific order because I was a researcher for a long time, and I thought it's the other way around, right? You start with the research and build it and they'll come kind of thinking, that's the 3 question mark, and then you have a business model. And that's not how it works. Right? So it's the other way around, and that's why these slides are in this way. That said, I will talk about the research first, right? Because it's an AI meeting. But it is very important, and I'm trying to stress this here, that you need to think about what the problem is you're trying to solve and talk to the people that actually have the problem before you start throwing a lot of GPUs at a problem that you think is worth all the time and resources that you throw at it. So we are a spin-off from the Australian Centre of Robotic Vision, which unfortunately doesn't exist anymore. Its funding stopped with the end of 2020. But it was a long-term national research initiative. Sue can talk about it a lot more. It was based in 4 universities here in Australia, so it was a really collaborative effort. It was an awesome place to be. And that's how I came to Australia about 6 years ago now. But it's based on a lot of the research that comes out of that, plus some research that I did before. And you build those modules, like it's a bit of an abstract way of thinking about it, but you build all these little parts that may or may not work together as a nice system. Because as a researcher, you don't necessarily care yet about the application, right? But you build all these modules. And at some point, you need to think of how can I use them and an impact outside of academia. We all, as academics, want citations, and the H-index is very important. But if you want to go beyond that, you have to start thinking, how do I take some of these modules and ideally think about a system, but it means taking huge amount of these modules in various aspects. And for us, the real focus was the brain, the eye, and the hand. The brain being the eye system, the eyes being the computer vision models, as well as the camera system, and the hands more on the mechanical side of things, as well as sensor integration on like actually doing the physical interaction. And this is a difference that we as an embodied AI system really put a lot of effort and emphasis to as well. We are highly reliant on that part, right? We can have the smartest AI. If it actually can't pick up the object, who cares? Because the problem that we are trying to solve is picking up a piece of fruit. So there was a lot of research going on. I was based here at QUT in the robotics lab. But as I said, it's like a national research initiative. And now we built all these things. So what do we do next, right? Like for me, it was taking a step back and trying to understand how you put them all together to build a system. And for me, the pivotal point for that was, and I'm going a bit more into the research now, pivotal point in that research for us was we had a challenge, and it's the Amazon Robotics Challenge that we entered. The challenge was, can we build a robotic system that I can actually do something as a system and not just detect a lot of objects or stow a lot of objects, but actually combine that and have the problem of order fulfillment solved, right? You see the shift there? It's not the problem of top 5 image classification that you're solving. The problem is you're trying to solve order fulfillment, which means the robot looks into a box, picks up an item, makes a decision of whether it is the right or the wrong item. Usually you should pick up the right item, and place them in a box. And that sounds really trivial, especially for us who pick up a lot of things every day and stick them in boxes. So I can tell you it's hard. You have to believe me on that. I've done this for a long time now. I started my PhD more than a decade ago on that with the idea that it can't be that hard to pick up a blue box. Turns out it's very hard. But the pivotal point for me was not so much that it's a hard problem. It's more the question of like, can we integrate these systems together into something that's actually useful? And that's something that a lot of researchers tend to ignore, right? Because systems are complex, systems are hard, experiments with systems is complicated. But so we entered the Amazon Robotics Challenge. We built this robot here that we called Cartman from scratch in about 6 months' time. Some of the people here in the room probably remember it, both the sweat and tears, but also hopefully the joys. But really sort of stumbling onto the problem was for me the moment where I realized that all this technology that we built is actually useful. Right? And that's something nice to hear as a researcher. So for me, that was really great. So we built this robotic system. We packed it up into suitcases, flew to Japan, built it up there again, ran the demo, and made it work. And in fact, we won the challenge, and we were the only team that managed to pack all the items that they picked. We were also close it better. Cool. We were also the only team that had a self-built robot that actually worked. That said, we broke the robot on the first day, so that's usually part of the challenge. And we were not in bad company, right? So there was like international, highly ranked universities, international corporations that did that. And as I said, I'm going to show some videos here and let's see if that works. So this is during one of the tasks that we had to do there, and you see a bunch of nervous university students there sitting in the background because it's a robot. It needs to do these things autonomously. So once you hit start, the only thing that you can press is that red button, and you should not press that red button. So what you see here is the robotic system looking into the box, deciding that this item is the item that we want to pick, picks it up with one of the end effectors. We have 2 end effectors on this one, and tries to place it in a box. And sometimes that's a bit more iffy than otherwise. And that was the state of 2017 robotic systems, right? So this is the robot that won, right? So this is not the slowest one. What you can see here is we have multiple end effectors. We have a vision system that, if you look very closely at the end effector, you can see a camera, the black T-looking thing there in the front. That's the camera looking down. And obviously it's not perfect because it's still a research robot. Let's stop it here. But what it showed me is that we can actually do these things. We can build those systems. And we can actually get them out there to do something useful. I want to play the other video too. Let's see if that works. Because as much as this is, I'll probably, yeah. As much as this is like an AI talk, and there's a lot of AI that we had used in the vision system. So it's a deep neural network that does image classification, object segmentation specifically, and we can compare that whether we do this as a supervised learning or an unsupervised learning, because Amazon brings in new objects on the day that you do the trials. So you can't really pre-train a neural network for a lot of these things. What I actually wanted to show is, where was it? Probably missed it. What we actually wanted to show is that even while this is an AI system, you have a bunch of students doing that. So it's not totally working yet, right? So you have a robotic system that learns, but it learns from these guys, kind of like a Formula One pit stop, putting in the hands. I can play it again because I like it. These people basically putting in objects, placing them in front of the camera so the system can learn how to visually identify it. Right? So you still need a human in the loop to some extent. Right? So it's not perfect, as I said before, but with a lot of engineering, you can actually make these things work. And that's really exciting, right? Because now all of a sudden we can actually solve problems that are out there, not just academic problems in terms of like creating new and wonderful papers that get cited or not. One of the things that is part of the challenge, as I mentioned before, is that you have a vision system that needs to classify objects. And I don't want to go too much into the detail of that one here, but what I want you guys to think about, and as a takeaway, is there's lots of ways that you can think about a problem. And you can, these days, especially in AI, get a lot of off-the-shelf image classification systems that would tell you these things. But it might not always be the right tool for the problem that you're trying to solve, right? So thinking about the problem actually might allow you to do things differently. And so what we did, for example, the top is just, like the output of the system. But how do you train these systems, right? Usually you label up the data, you send it through a network, do some backprop for hours, and then you test the system and see what the accuracy is. But even there's a question, how do you measure accuracy? Sure, question. Sorry, the question was the bottom one, where 100%, why is it not the whole image?
You give it the picture of the whole thing.
I'll go into that in just a second. Good question. So my point was, what is accuracy? And that's exactly that point down there, right? What is it that you actually want to get out of your neural network? And what is relevant for the task that you do? Because for image classification, intersection over union, who knows what intersection over union is? Has a few hands up. Okay. Intersection over union. Okay. It's a way that classifies pixels, right? So you have a ground truth image, and you have the image that comes out of your neural network. So how do you now compare whether you classify the object correctly or not? If you classify the whole image and say a cat is a cat and a dog is a dog, it's simple, because you have basically a one output that says cat or not cat. If you do it on a pixel level, each pixel you need to classify whether that is now the rightly correct classified object or not. But then you have the question, how do you compare all these pixels with your ground truth? Do you just count the ones that appear in both, which is intersection over union? Or do you do something more fancy? What is your true positives? What's your false positives? How do you combine these metrics? And there's a bunch of metrics out there. Academics have explored that for a long time in optimization, not just in neural networks. So you can go out there and look at 20, 50, 60-year-old studies about what is a good metric to optimize on. Cool. The question was, what's the difference between the 63% and this 83%? And this 100%. Cool. Yeah, I'm going to go into that just now. So the difference is, or the question was, what's the difference between that number here and this number here? So first of all, these four numbers are different metrics that can tell you how accurate your neural network is. So they don't have anything to do with the structure of the neural network. It's more a question comparing your ground truth to what the output of the neural network is, which usually then use as a classification system to understand how much longer you have to do backpropagation. What I want to stress here, and we just can compare these two here, if you have a system that says all the pixels that are, this is a bag of socks for those people that haven't identified it yet, how many pixels of that bag of socks does your classification neural network classify correctly, right? So in this point, you say 57 here with the intersection over union and 63 with the F score. Doesn't matter those 5% difference, but it's basically, as you mentioned, partly because it classifies some pixels that are wrong. Same thing here, it classifies some pixels as wrong because technically they belong to the object. But, and this is now the important point, if you're a robotic system, it doesn't matter if all the pixels are correct or not. But it matters that those pixels that you think are correct are actually on the object that you're picking. Yeah? Because if I now give this to a grass module, all the pixels here are on the right object. All the pixels here are on the right objects, but there's 50% of pixels that are on the wrong object, which gives you a very high chance that if you pick one of these pixels, you're picking up the wrong object. Yeah? So the question is, what is the right metric for the task? Doesn't matter mathematically if you understand what an F half score versus an F1 score is. But the critical point is, like, think about your problem and, understanding which part you can actually optimize gives you a different insight and gives you potentially a challenge-winning advantage. As in our case, we trained our system with that score and it works for us. That doesn't mean that it's the only score that works here, right? I'm just trying to tell you that sometimes it's very important to think about your problem before just throwing an off-the-shelf neural network at a thing, or just taking what other people are doing and test it in a different environment. This might lead to very different outcomes, right? Any other questions on that? Because that seems to be interesting to people, so yeah. Very good question. So the question was, what is the order of things in terms of depth far away from you is actually critical if you're doing object manipulation. It's actually also critical. Exactly, you can assign a weight, but it's the same problem, actually the same problem occurs for when you're a self-driving car and you want to estimate how far things are away, you still want to make that decision. What we do in our case, we do have a specific item that we want to pick. And in that case, it actually is slightly different to the weighing and just the machine learning in a car, because, and I mentioned that briefly before, you want to pick up the object that you want to pack, but sometimes you might not see the object that you want to pack because it's covered by a bag of socks. We don't actually know what's behind the bag of socks, but I might know that none of the object in the box is the thing that I want to pick up. Yeah, so the comment was, there's different views, so because these objects are different size and they might change views, and that also informs the system that we're using. But it's also, you need to have a strategy, and in our case, that was not an AI strategy, it was somebody smart, I think Doug also implemented the last minute, where it's kind of like a Tetris thing and like figures out like none of the objects are there, so I'm picking up something and place it somewhere else and see if there's something underneath it. And sort of have this, I call them strategy or behaviors that you need to fall back to that are outside of the AI. And if you're working on an embedded AI startup like we do, there's lots of engineering, there's lots of strategies that we at some point would like to throw an AI system at it, but for a product, you just need to make them work first, right? So very good point. In this case, We didn't have too many of the problems with different size spacing, if I remember correctly. No? Oh, okay. Ricardo over there was working on the vision system, so that's why I'm asking him, because I don't remember all these things. Cool. Any more questions on this one? Otherwise, I go to the next slide.
I have a question. So one of these systems, you've obviously got a number of different tasks. One is looking at what's below the robot. You've got to figure out, what the objects are, where do you pick them up. Maybe when you place them, you have to choose where, so kind of like a bin packing problem. Can you explain what are some of the core components that go into a system like this, at least today, with today's technology?
Yeah, no, that's a very good point. I'll give you a short answer, and we can discuss this over beers in longer terms. The short answer is we want to design systems that are sort of broadly applicable. So we're thinking in terms of layers, and that's not neural network layers, but like abstraction layers or task layers, for lack of a better word. It is also highly dependent on the problem that you solve. So that's sort of two separate issues. And that's sort of, I go back to the previous slide, maybe that one. Yeah. Let's imagine that all the orange ones are brain parts, like machine learning algorithms that make a decision, maybe for example, a fallback strategy that was just mentioned before. Now the problem is, first of all, you need to develop those. But secondly, you need to also pick which ones of those are relevant for my task. We don't do the second part by AI or machine learning at this point in time. They are specifically picked by engineers for that specific task. If you think about, let's pick the avocado packing task, because it's actually a bit easier to imagine than the Amazon task. The avocado rolls down, and I can play the video at the same time, hopefully. The avocado rolls down the shaft there and sort of bubbles around a bit. The first thing that we need to do is find out where the avocado is. So we do an object detection, image segmentation, localization of where that is. But that's not good enough to grasp it. So we have a second system, which sort of, for me, now thinking is sort of the next layer. It's a grasping module that makes a decision based on the avocado shape and orientation. What is a good way of putting that suction cup, or in the other videos you've seen the pins grasper. Where is that I want to pick it up from? And that is partly learned and partly engineered. And again, we have different modules where we can fall back depending on, they're actually slightly different if you're a sweet potato versus an avocado, because it turns out sweet potatoes are very uniquely shaped, let's put it that. But then you're still only halfway there. You then need to actually control your robotic system to get to this point, and you might actually have an error in that too. So we can use something called visual serving to reduce that error if that's needed. Then we finally have the object in our hand, right? And again, we're still not there, because now we need to find a way out of the box or out of the shaft here with the avocado, which is a motion planning problem. Identify, or at least keep in memory, which ones of the box spots over here are full and which ones are empty. Plan a trajectory there again, motion planning. Control of moving the robot there. And at this point in time, we just place it, and we actually take a secondary image just to verify that we placed it. So there's not a lot more smarts on this side of things. But that said, talking to farmers, what you would like to do is, label it, put a QR tag on it, quality assurance, traceability issues. So there's a lot of other things that we can do afterwards. But so right now, that's sort of the flow. And as I said, there's, I guess, like 3 layers, if you want to think about it, with different modules activated in different paths, which may or may not be the same thing for picking up and placing it down. That was actually the short answer. Sorry. Very good question. What do we code this all in? Whatever is the flavor of the month. No, just kidding. Software in Python, hardware in C++, like hardware and firmware in C++ and C, and a bunch of things in whatever people enjoy in the middle for like testing. So we still have one person that uses MATLAB, mainly Peter. But yeah, so depending on where they are in different parts. So I guess 90% is probably Python and C++. Yes, it works reasonably well for prototyping and debugging as well. question is, do we monitor our robots online through the cloud? Yes, we do, although right now we don't have them externally facing in the cloud. We only have an internal network of computers. So the question is, on a farm, do we actually get internet access or not? So we have local information that we're storing that we can upload to the cloud whenever we get internet access, which turns out is a separate engineering problem again. Sorry. Very good question. What do we do when an avocado comes down that is damaged or not according? Actually, these boxes tend to be in qualities of different quality grades. We can do that. We have so far not done this for customers because there's a machine before it that technically should do that. And I say technically because there's still errors in there. So it's something that we're discussing with them if that is a value add-on. The other thing is we can reclassify the quality of the avocado because there's a machine that does that before it, but there might be variability because it's a machine, there might be errors to it. So what they've seen is, I don't know, I've learned so much about avocados in the last 12 months. But there's webbing on avocados that is very hard to detect with vision system, but it's basically a slight web of kind of like veins on the avocado, and that actually doesn't change the quality of the fruit, but it changes the margin that you get. So if you can sort that out, that is helpful. And sunburns tend to happen on the bottom or the top, like ground burn or sunburn. And that's something that the current system is actually not looking at. So that's something else that we're looking at. But in short, we can do that. In practice, we have not need to deploy that yet.
You mentioned avocado grades. Did you have any differences between
the question is grading of avocados, and did we have any particular problems with it? Yes, we packed an avocilla, which kind of was like almost like a, I don't know, a massive piece of fruit, almost banana shaped kind of stuff. And then there's questions of like, first of all, can you still pack it into the box? Secondly, how do you pick it up nicely? So that's sort of one of the biggest issues that we have. Generally, I would say we have covered a significantly large area of fruit and produce that we are pretty comfortable with. But as any other machine, there's going to be some edge cases that we currently cannot handle, and it's mainly on the mechanical side of things, right? If it's too small or too large for our gripper that's currently installed, we can't really do anything about it. We have ideas of how to change grippers on the fly, but it's also a question of throughput, right? If you need to do that, you're actually lowering your throughput. Is that a trade-off that they're willing to do or not from a customer point of view? No. Nobody's got time for that. So the question was, do we video 100,000 people packing avocados? No, turns out this avocado packing is not that hard. So yeah, we don't video people doing it. We're also not having a hand, so there's not really a lot of information there. We do take pictures of lots of avocados though. There was another question over here. Very good question. The question is like, how do we integrate into warehouse management system or the equivalent for a packing shed? So there's adapters that we have, but there's also a question how currently people are reporting that. It's manual. So we can provide printouts or emails and stuff like this. So depends on the current system. The guy quite literally said he wants to sit at home on the couch and control his packing shed. We're probably a bit far away from that, a couple of years, but yes, good question. Two more questions back there if somebody wants to run up with a microphone. How are we doing on time, by the way? Because I've only been at the very beginning of my talk.
This might sound a bit funny, but I just noticed like the avocados are labeled, right?
Yes.
So that means like the object detection and the label placement is already sorted before it actually gets to your thing. I mean, I'm just trying to understand like. So is it only the grasping thing that technically needs to be solved from your system?
So just to clarify, there's a sticker on that one, but it's a marketing sticker, right? It just says, in this case, Sunny Spot Packing or Evolution, which is their brand. So And that's automatically done. That's actually a really cool mechanized solution with like just sticking things on whatever passes through. That doesn't help us with image classification or localization. In fact, it actually sometimes disturbs our image classification and localization because there's a different color right in the middle of where we want to pick it up. But what we need to solve is actually, like, and actually you saw it on that last avocado, the sticker is not always facing us, right? So we can't really look at it. It's similar if you think of the Amazon use case, they all have barcodes, but that doesn't mean it makes it easier, right? Because can you see the barcode in the first place? If you know the barcode, does that help you? And what do you do if you can't see the barcode? So it's like the chicken and the egg problem in a way. So in this case, we also don't rely on that. So we basically need to do every object classification as well ourselves.
Yeah, sorry, maybe like I was thinking like when the label is actually placed, whatever the system actually placed that label, wouldn't it have actually solved the object detection and the placement? Or do they just do it blindly?
You do it blindly. So that's
okay.
A mechanized solution where basically the avocado is squashed through and the label is stuck on. So
got it.
There's some really interesting mechanized solution out there. They're not particularly smart, but they solve a very big problem. So you don't need AI for everything. It's a dynamic environment, things roll around, and that can be very tricky sometimes, especially if you start moving and then somebody decides another avocado is coming through. But yeah, we can't really control that. What's another question?
Yep, and my question is, what's the ROI of implementing this robotic system instead of like having one person there or, I don't know, like 1,000 tons of avocados?
Well, that's our black magic, isn't it? No, what we aim for is to have a robotic system that is over a day at the same throughput than a human, at the same cost than a human. And we can guarantee that for some produce. Obviously, it's a question of margin, right? So some avocados is about like $1 or so a box in terms of packing cost. So we can compete with that. But other fruit are either very cheap, like oranges, because they're actually usually bagged and not placed precisely. So the business side of things makes only sense in some cases, right? But where we are right now is that in those use cases, we can, on a daily basis, roughly pack the same amount of produce at the same cost than a human packer.
I think the only question left is what your favorite avocado dish is. Let's keep moving, and we might save the questions to the end, guys. Just conscious of time.
No, it's okay. That's all good questions. I'm going to go through some of the other slides, but I'm happy to take some of these questions. Just to recap, we're on the research side of still things, right? So we haven't gotten to the product part yet. The other part that I want to talk about, just because it's a cool application and we got lots of sites out of it, and Doug did a really awesome job doing that, is, and it sort of came up before, the other side. So the vision system is only giving you one part of the problem. It gives you where the fruit is, but it doesn't tell you how to pick up the fruit. It doesn't even tell you what the geometry of the fruit is. So what we looked at was how can we, and this is not a new problem, right? People have looked at robotic grasping since they built robots, so like about 60 years ago. But with deep learning technologies and machine learning and computer vision systems that are actually cheap and somewhat reliable at this point in time, the question was, can we integrate those systems in a time frame that actually makes sense for a robot to deal with exactly what you mentioned before, a rolling avocado? A lot of robotic systems are still sort of like looking at the world, make an assumption of like, this is a geometry that I know, and then I figure out where it is, and I basically close their eyes and stick their hand in and try to pick it up. And we've seen a lot of that in the Amazon challenge. And so Doug's research afterwards was like, how can we close this loop? We want to have a neural network in the middle, or actually in the end, it doesn't matter if it's a neural network, right? We want to have a classifier in the middle that tells us what a good grasp point is, where that is with respect to where I am, and then close the research loop, close the control loop of the robot, so I can actually get to this even if things are changing. And why is that important? Because the world keeps changing, right? So we can't rely on, especially picking in the field that we eventually want to do, can't rely on everything just being stationary. Just showing a video because I'm aware that we're running out of time, but I promised robot videos. Turns out, yes, you can do that. And you can train a neural network that gives you classification quality across an image, pixelated image, that then tells you where to pick things up. And this being a research project, obviously you need to have like some reliable way of testing that. So we put whatever we could find in the lab in a pile and then moved it around and showed that the robotic system can adapt to that change. Furthermore, the same neural network doesn't really care what kind of thing you throw in front of it. That's sort of a bit of a side effect, but what that basically means is you have now a rather primitive but fast way of picking up something without knowing what it is. And again, by thinking about the problem differently and not just thinking about I know what I need to pick up and then I design a system that can do it, but like thinking about the problem slightly different, that came up with this cool way of thinking about how can we get a system, in this case a neural network, to give information at high enough rates that the robot can actually be controlled to do this. And as you can see, there's some wobble in there, there's things rolling around, but we still managed to pick these things up. I'm not going to go too much into detail in here because of time, but as I said, I'm more than happy to discuss this afterwards. The lesson learned from the last, probably too long talking, on research was it pays off to think differently. And I know I stole that, right? But it pays off to think about the problem that you're trying to solve and understand what is the critical problem or part of the problem that actually can think in different ways. We built our own robotic system, which was a Cartesian robotic system, which is not like the robots that you see out there. We thought about our method of classifying what we're picking up differently. It doesn't change the structure of the neural network or change the structure of the machine learning problem, but it turns out it makes a huge difference for the grasping. And then we played around with like, how do we do this grasp quality in a more quickly adaptive way that actually allows us to react to changes in the environment. And for us, from a research point of view, and also from a Lyro point of view, that has really has a big trade-off for us. So I want you guys to keep thinking about that. Changing the pace slightly differently, and I know we have to go through this a bit faster, so I'm going to skip some of the non-so-AI interesting things. As Lyro, nobody cares if there's a deep learned neural network or a reactive GGCNN or whatever in there. They care that you can pack up quite literally everything that you throw in front of it. And so we branded that as Lyro Machine Intelligence. And it is this combination of the brain, the eyes, and the hand, and all the stuff that I mentioned before, plus many more things. The interesting thing on the bottom is the same system works across different robots. There's actually 3 different robots down there from 3 different manufacturers, one being us, and also has different grippers. And that's sort of coming back to the modular approach that I mentioned before. In transferring these things into the real world or into, I guess that's the QT tagline, but transferring that into a real application, there's certain difference in thinking and difference in focus that you want to do. A lot of research focuses on narrow parts. And in our case, specifically around grasping, a lot of focus is on how do I move things, how do I pick things. Not so much is about how do I pack things. From a more theoretical thing, people have looked at bin packing and optimizing that. But like, how do I do that on a real robotic system has somewhat been underserved by the research community. So we as Lyro saw that as an opportunity to explore that. And so a lot of our R&D is more focused on a systems perspective, which again makes sense, right? Because we're selling a product, which is a system, not a specific subset of that problem. And I've mentioned that before. The point is we're building a product, not the technology behind it. That's not what we sell, right? Yes, we're doing technology improvements, and yes, there's certain things in there, and that enables us to, for example, have like 3 different robots in more or less the same shell, doing the same task, just with different ROI calculations and with different business models behind it. This is our current robot. Who thinks it looks sexy? Cool, thanks guys. Yeah, it's, from my point of view, it's just really exciting to see these things turning into systems that are actually useful and helpful and can do things out there. The other thing, and this sort of ties in with the whole title, so yeah, about half an hour in, we finally got there. The problem is you want to build something that can actually be deployed in thousands of robots. And how do you do that? How do you start tackling that problem? And it's not something that you can just add on afterwards. Right? So we need to think from the beginning, like how do we build enough robots out there to tackle those 26,000 jobs that are missing? And I'm not going to go into detail. I'm happy to chat about it afterwards. There's a lot of manufacturing on optimization on that side of things. But a lesson learned is large problems are large, and there's a reason for that. But it also offers you an opportunity because you can actually do things that otherwise you thought you couldn't do. And I'm going to skip that one. I already mentioned that no one cares about your tech, right? The other thing is wide and narrow do not contradict, right? So, and I'm happy to discuss this a bit further, but in short is building technology that is widely applicable is very good because you can scale it up and use what I just said before about large problems. But to build it for specific use cases, you tend to be very narrow and need to focus on very narrow aspects. I tried to make this look a bit more interesting. Unfortunately, I didn't. But the idea is you don't just think differently about the AI systems that you build, but also about how you manage them and how you build modules that can either be used, in sequence, in parallel, smashed together, whatever you want to do. And how do you spend and plan out your resourcing actually can allow you to think both wide and narrow at the same time. If you have a system that is modular and you can tackle a lot of problems with, that's very great. But it's not a product, but it might enable you to tackle multiple products at the same time that really gives you that scale. And I understand that it was a bit short, but we can go into this a bit later, because there's another point that I want to make. Hardware is not software. Hardware is called hardware, and some people say that's because it's hard. I don't think it is. I think it's because software was named soft, and then they figured out hardware is the opposite of that. But that's not just meaning it's hard and don't do it. It actually offers you opportunity to, again, think differently about your problem, think in ways that make sense for the problem. So you might have a limited budget in terms of power, in terms of compute, in terms of heat, which, to be honest, we didn't think about. But that actually leads you to asking questions that other people might not do. And that can give you a significant advantage. And I think that's a really good opportunity, especially here in Brisbane, where we have a significant amount of roboticists between CSIRO, QT, UQ now. So I mean, there's heaps of us. But it's really an opportunity because it puts you in a different mindset. And I think that is something that is very exciting. And actually, I didn't even talk about the picture. There's something called DevOps in computer vision, in software engineering and machine learning. We have a very similar approach to trialing out hardware very quickly and test it. And I think that's something else that's very interesting. And again, that's something that only has been enabled probably in the last decade or so with 3D printing and rapid manufacturing, where you can actually test things out. The story that we tell, and Ricardo can maybe disagree, but during the Amazon challenge, we changed the gripper 30 times. The CAD designs of the gripper changed 30 times in 6 months. And we tested a lot of them. We probably didn't test all 30, to be honest. We tested a lot of them by 3D printing them and sticking them on a robot and see if they worked or not. And that is valuable data. And I'm not just talking about like the machine learning data, but also data for the engineers to understand how things work. I think that's really a massive opportunity. For example, our robots, right? As I said, they look pretty sexy right now. The first one did not. I mean, you can disagree with me, but it's an MVP, right? It doesn't have to look sexy. More robot videos, and I'll just leave it here. Wow, right on time. Thanks for being here. I'm gonna still stick around, so if you have any other questions. I think we have time for one or two, probably. Cool. Thank you.
Any questions, guys?
Hey, the hardware you were talking about briefly, when you guys write the code, depending on the hardware and the manufacturer, some of the hardware you're using is all coming from different manufacturers. And you were saying something about narrow, wide. It's almost like you're talking about an operating system for robotics now, where you can just plug it all in and it's got the drivers built in, ready to go with all the different hardware.
Yes, what's the question? No, no, there is actually something called the robot operating system, which is actually just the middleware, not a robot operating system. But abstractions and layers. I mean, it is very much like an operating system in terms of thinking like 80s, 90s operating systems. You know, you needed to know, for MS-DOS, you needed to know where in the physical memory of your hard disk your things were stored. All of a sudden you had a file system that was doing that for you, which allowed you to abstract that thing. Similarly, you can do the same thing with motors, right? So yes, not every motor is going to give you exactly the right signal, but you can abstract, for example, what you want to do, position control, velocity control, and then just have an adapter in the middle that basically turns your high-level thing into what actually the control understands. For me, the really exciting thing is, hopefully very soon, we can write adapters that are machine learned. So they can adapt on the fly because they are a new thing we just plug in and we don't even have to write the adapter ourselves for it because it knows roughly what it needs to expect and can do that, hopefully autonomous. For me, that's a very exciting research area for machine learning. But yes, thanks for that. We're doing that and we think it's cool. More people should be doing it, but yeah.
Juxi, you mentioned learning on the fly. Good time to jump in. There's obviously a lot of papers about reinforcement learning, particularly from Google and some of the bigger companies who have lots of resources at their disposal. For smaller players, is it mature? Is it ready? And you know, are you guys using it in your product? How far away is it?
Very good question.
Potentially end-to-end reinforcement learning.
End-to-end reinforcement learning is far away, I would say. I like the approaches that Google and you know with the ARM farm, but also OpenAI and so are doing with like large-scale data collection. I think it's not the right way because I think it's thinking like a computer vision machine learner and putting it on a robot. I think that's sort of what I was trying to hammer in with the slide that actually had a lot of questions. Thank you for all of you for that. I think two things. I think reinforcement learning is awesome, but it sucks. And we can discuss this later on, but I think the beauty of a reinforcement learning description is that it's very simple, very easy to understand, very mathematically simple, with the drawback that it hardly ever works. And that's why you look at any reinforcement learning paper, they're doing the cool MDP, POMDP description, and then you have like half a paper describing how they need to prepare the data that goes in or do stuff that comes out of that thing before it becomes actually a POMDP. So as a researcher, I think there's a lot of research to be done, which is exciting. As a practitioner in a company, I think there's ways where you can apply reinforcement learning in the right way, and we're looking at some of them. End-to-end, purely blindly motor babbling your way to a target is not the way to go.
On the on that statement you had on wide and narrow do not contradict. Like when you look at your business model, are you positioning yourself like a software as a service type, sort of comparative to a human being? And like, you know, if you go down that path, you know, and you're selling avocados, then, you know, or picking avocados, you kind of have to kind of perfect and make it as good or better than a human being, like which goes down the narrow path. How do you go back to the wide path, and you know, how do you manage that to source funding for your organization, like between the wide, narrow applications and revenue?
Yeah, very good question, and thanks for bringing that up. I did go a bit quick over the wide and narrow, but exactly what you said, I think for me is one of the reasons why you should do both. The wide part, let's start with the narrow part. You're totally correct. If you want to focus purely on avocado, you can solve it by simplifying the problem and pushing really forward. You can do that by improving your machine learning system and vision systems, what everybody else is doing as well. You can do it by improving your hardware system, so you can really push down there. But it turns out, if you do that, you end up with a solution that is highly specific and highly mechanized that works on one farm and not on the next. And it might even just work for dispatch of avocados, but not for the next one that comes in. Fruit and other fresh produce is actually really interesting from that point of view, because there is no one model that fits even one type of fruit. Like even avocados, you have like Hass and Shepherd avocados, right? So they're different even in color, right? So one system is not gonna be applicable to lots of other things. And so there's a question actually from a business model. I think it's a very valid question. Why are you not going down this route? And you partly answered it already, because if you do it, you're overfitting to a very small problem, to use machine learning type terminology here. You're overfitting for this, and it's not going to work on any other farm. So at this point in time, you're a consultant, one solution kind of provider, which people are doing, and they totally should. So I'm not saying they shouldn't. But from our point of view, it's not the fit for the technology that we have, because we have started with a wider technology. And from a business point of view, we want to really have 100,000 robots out there. They all can't be very specific robots. Because the other problem from the business side of things, and I'm babbling on, but like the robots as a service model that you mentioned before, where we basically rent out the robot, only flies if you have a cheap enough robotic solution that can be applicable to lots of different problems. Because most of fresh produce is seasonal. All right, so that means you can pack maybe avocados for 3 months of a year here in Queensland, and then move to New South Wales and probably eventually Victoria, and you get like 5-6 months out of a year. But what do you do with the other 6 months? And that's why we haven't seen a lot of agricultural automation yet, because the farmers are also not, saying like, I'm not paying for something that I use 6 months a year, unless it's cheap enough, right? And so they're doing their own ROI calculations. So that's where I think the narrow and the wide for me comes together. And the wide for me falls back to these different modules. In terms of avocado, you can have a shepherd avocado module and a Haas avocado module that are very specific for the specific instances. But if you build a system behind it that is modular enough, you can swap them over, hopefully very quickly. And then you just, you feed back to the system alone improves, fine. But the data that you collect on your robot operations and other things feed back into other parts of the system, actually probably like a reinforcement learning problem if you discount it over the different modules. But that's going to mathematical. But the point is, you can, by each application, though it might just optimize a small part from initial thought, still learn the other things that you have a wide application to. Does that make sense? If not, we can have a beer, discuss it then. Everybody questioned out? No, there was one more over there. Cool. I'll paraphrase that for the audience that hasn't had the microphone. The question is, if you look at the avocado example, the thing rolls down. Can you use that information to get smarter about how to pick up an avocado, or even separate them to other produce? Short answer is yes. You can totally do that. Long answer is it depends. And it's a question of trade-off. We do collect a lot of data that we're currently also not even using in our current product, but we see the value of that. And as a roboticist, I'm very interested to use data with temporal information, because sensors do provide temporal information, and a lot of computer vision researchers still don't use that. So I very much would like to do that. I think your hand up was first. The question was, how many arms do you need, in short? A lot of robot arms are singulated arms, and we use a single arm here. There is definitely application areas where you want multiple arms. There's definitely application areas where you don't want a Cartesian robotic system as well. Like you mentioned foliage, it in-field operation. You might actually need an elbow to operate that. So yes, there is, and yes, there's a trade-off. The question that we very often get is like, why are you not using a super fast robot arm? Or why are you not using 3 robot arms in parallel? And the answer from our point is, it doesn't matter. The question is not how much is your throughput. The question is, how much does each piece that you pick cost you? Because you can, not always, but most of the time, actually deal with the throughput problem by putting in multiple people, multiple robots, multiple arms. So the problem is, from an ROI point of view and a business point of view, what is the cost per pick? And is that competitive enough to the human labor? Then you can scale it out afterwards, but it's not the speed of the robot that matters as much. Oh, I thought you meant the person, but sorry, yeah. No, yeah, how much processing power does that robot have? So we are running this off a stock standard desktop GPU from 2 years ago. And we don't need that. So we are working on a more embedded system solution. NVIDIA has a partnership with us, or we have a partnership with NVIDIA. I guess they're larger, but still at this point in time. But so we have a range of graphics cards that we are working with. In the current, so this trial was about 6 months ago. So basically it was a desktop computer that we took with us that plugs in. In the current product, it is actually an embedded, well, hardened site computer. It's still more like a desktop computer. For some of the other application areas, we're thinking of embedded systems that are small enough that you actually strap it onto the robot that just purely does the vision system, and some other high-level function might be running on the controller of the robot or somewhere else.
I think we'll finish it there. If you have any more questions, feel free to go have a chat to Juxi. Juxi, any closing thoughts?
There's an email address. There's even a phone number. I don't know why I have that one there. But feel free to reach out, send an email. I'm happy to have a chat or a coffee or a beer. And I'll still stick around definitely for a bit here. So thank you.